In the last two videos, we dealt with the prediction equations, how to take the state vector x and the uncertainty matrix P from the current state to the next state. What we want to do in this video is to talk about the measurement or the update phase of the Kalman filter. In order to talk about the measurement phase, let's go back to what we already know. If you remember, the Kalman filter is the weighted average between the prediction based on the motion model and the measurement. So, this is my robot at time k, and the motion model predicts that at time k plus 1, I will be over here. Remember, it's just a prediction. Now, what happens is that I get a measurement from the sensor, and the measurement from the sensor shows me that my robot is located here. Maybe it's sad because it's not where I thought it was. The question is, what do I do? So again, if you remember, the Kalman filter is the weighted average. I take this guess, which can be represented as a Gaussian distribution, and I take this measurement guess as can also be described using a Gaussian distribution, and I multiply them together, which ends in this much more accurate Gaussian distribution. This is the posterior. And the weighted average is based on the Kalman gain. When the Kalman gain goes to 0, I will give more weight to the prediction, and when the Kalman gain goes to 1, I will give more weight to the measurement. This is exactly what to do. The problem or the challenge is what to do when we talk about x as a vector, meaning x that has several dimensions. Now, it's not so simple. Why? Because not always will my sensors be able to measure x1, x2, x3, all the way to xn. So let's see how this is expressed graphically. The left graph we already know, but the idea is such. The left graph is the state space. This graph now is in 2 dimensions, but it can be in 3, 4, 5, or even 10 dimensions, where every dimension describes one of the parameters of the state vector. But what I'm really measuring is not the state vector, is the sensor space. So I can write here sensor 1 and here sensor 2. And therefore, when I have some point in my state space, and remember, this doesn't have to be 2-dimensional, it can be 3, 4, 5, or even 10 dimensions. What I need to do is to transfer this point from the state space to the sensor space. This transfer, as you probably assume, must be linear, and this transfer will be called the H matrix. The H matrix takes the state vector and transfers it into the sensor space. Now, because it's not clear what the sensor space is, let's give a concrete example. Assume that our state space contains position and velocity in 1D. This means that we have 2 variables. The first is the position and the second is velocity. But my sensor cannot measure velocity. My sensor can only measure the position. So, if my sensor only gives position, what will H look like? Matrix H is supposed to take the state vector, the position and velocity, and change it to position only. So what do you think? The answer is very interesting. The H matrix looks like this. H equals 1, 0. Why? Because if I multiply, what I get is 1 times position plus 0 times velocity, which basically is position. And this is exactly what I get from the sensors. Just one measurement, the position. And you can also see it via the dimensions of the matrices. Here we have 1 by 2, and here we have 2 by 1. So if I multiply 1 by 2 by 2 by 1, I get 1 by 1. Sometimes the sensor space cannot measure all the options in the state space, and therefore we need to fit the state space into the sensor space. Usually it will be a simple fitting of 0 and 1, whether we measure in it or not. Now a question. Assume that I had two sensors, one that measures position and another that measures velocity. What is h in this scenario? The answer is very simple. When I have two sensors, or when I have n sensors, so every one of them measure a point in the state vector, the H matrix becomes the identity matrix. Let's write it. When this matrix is multiplied by the state vector, what we will get is, again, position and velocity. And again, you can check via the dimensions. This is 2 by 2 and this is 2 by 1. And when you multiply those, you will get 2 by 1. A measurement vector of two parameters, the position and velocity. In this case, I say that the sensor space is identical to the state space. Simply put, I have a sensor for each one of the things that I'm measuring in the state vector. Now, a different, slightly harder question. What would have happened if matrix H was 1, 1? So let's multiply the H matrix by the X vector. And what we will end up with is a single parameter, which is position plus velocity. What does it mean? It means that I have a sensor that can measure in one single measurement the value of the position plus the value of the velocity. These are not two different measurements, because two separate measurements would have brought me to 2 by 1 vector, as we saw earlier. This is one measurement that gets me a single value, which is the sum of the position and velocity. So when we understand, we can wrap it up. We can say the following thing. Mu expected, which is what we expect the sensor to show us, is h times xk, the predicted x that we have already covered in the last videos. Why do I put the hat over the x? Because it's the predicted x. This is not the real value of x. This is just the prediction of the state vector to the next state. And this is mu expected. This is what I expect to see in the sensor space. And again, the H matrix transfers the X vector to the sensor space. And sigma expected, the new uncertainty described in the world of the sensors, is hk times pk times hk transpose. Exactly what we did in the last previous section with the prediction state. So bear in mind that this p over here is basically f times p k minus 1 times f transpose. This is, again, we had the initial state vector at t equals k minus 1, and then we used the f matrix to take it from k minus 1 to k, and then we updated the uncertainty using these equations, and then we transfer it from the state space to the sensor space. These two equations take the prediction state and transfer it to the sensor space. In the next video, we will get the measurement from the sensor, and together we will see how we synchronize those two distributions, the one from the predicted state and the actual measurement.